In this video, we are going to look at what chemical reactions are and how we can generate numerical representations of these. And we will see that this process is quite similar to what we have seen for small molecules. We will first look at what chemical reactions are. A formal definition of a chemical reaction is a process where substances, the reactants, interact to form different substances, the products. In the context of biochemistry and enzymatic reactions, the term substrates is often used synonymously with reactants. The process of forming different substances is achieved by breaking, forming, and rearranging bonds. You can see an example of a chemical reaction here describing the combustion of methane. We see that bonds are broken down and rearranged to form carbon dioxide and water from methane and oxygen. The law of conservation states that during a chemical reaction, matter can neither be created nor destroyed, which means that the number and type of atoms must be the same on the reactant side and on the product side. We can see that this is also the case for the example displayed here. We have a total of 4 hydrogen atoms, 4 oxygen atoms, and 1 carbon atom on both sides of the reactions. Chemical reactions are initiated when reactant molecules interact in a way that leads to breaking and forming bonds, transforming the reactants into new substances, the products. This process often requires an initial input of energy or the presence of a catalyst to get started. We are now shortly discussing 3 common ways chemical reactions are initiated. Catalytic reactions are initiated by the presence of a catalyst, a substance that speeds up chemical reactions without being consumed in the process. For example, a catalyst can bind to 1 or more reactants, and this can change the shape of the reactants or bring the reactants in close proximity. Enzyme-catalyzed reactions are similar to catalytic reactions. Enzymes accelerate chemical reactions by binding to the reactants, which are in the case of enzyme-catalyzed reactions also called the substrates. This helps, for example, to correctly position the substrates, making it easier for them to react and thus reducing the energy required for the reaction to proceed. And then we have thermal reactions, which are initiated by heat. Increasing the temperature of the reactants increases the energy of the molecules, making collisions between them more likely and more energetic. We have seen that we can use smile strings to represent single small molecules, and we can do the same for chemical reactions by adding 2 additional characters to our set of characters for representing smile strings. On the one hand, this is a single dot for separating the reactants and also for separating the products. So if we have, for example, 2 reactants, we can write the smile string for the first reactant, then a dot, and then the smile string of the second reactant. And on the other hand, we can use a double greater than sign to separate the reactants from the products. So let's have a look at an example. Here we have again our methane combustion reaction, and below the reactants and the products I'm adding the smile strings of these molecules. We see, for example, that we have for methane a single C because we can infer the 4 missing hydrogen atoms, and similarly we write a single O for water because we can infer the missing 2 hydrogen atoms as well. We now combine this into a reaction smile string. We see that we separate the reactants on the left by dots, and since we have 2 times oxygen in the reaction equation, we list it twice here. Then we use the double greater than sign to separate the reactants from the products, and we again separate the smile strings of the product molecules by dots. We're now going to look at how we can numerically encode information about the whole chemical reaction, which can consist of multiple reactants and multiple products, as in this example. We're first going to look at 2 separate approaches that do not require deep learning models, and afterwards we will look at how we can generate deep learning based numerical representations. One approach to calculate a reaction representation is to first calculate a representation for each reactant and product, and then combining the representations into a single numerical vector. This can be best achieved using binary representations for each small molecule, which we get if we use expert-crafted molecular fingerprints. we can then calculate the sum of all reactant vectors and the sum of all product vectors to obtain a single reactant and a single product vector. Then we can subtract the product vector from the substrate vector, resulting in the single reaction vector with positive and negative integers. Positive integers indicate that certain properties or substructures are present in the substrates or in the reactants, but not in the products. And negative integers indicate that certain properties or structures are present on the product side that have not been present on the reactant side. Hence, this vector is a good representation for what kind of chemical reaction is happening. For mapping the individual small molecules to binary fingerprints, one can use different methods, including those that we have discussed in an earlier video, for example, the ECFPs or the RD-kit fingerprints. The next option we are looking at is a little bit similar to the RD-kit fingerprints for small molecules. As a reminder, for the RD-kit fingerprint, all subgraphs of a molecule are identified up to a specific size, and then it was encoded in a binary vector what kind of subgraphs were found in the molecule graph. The procedure for the differential reaction fingerprints, or short DRFP, is quite similar. We also represent all small molecules that are part of the reaction as graphs, and then we identify all subgraphs up to a specific size in all those molecules. Here you see an example for a few subgraphs in the product starting from a specific atom. We would do this for all reactants and all products. Then we note what kind of subgraphs we have found. The reactant subgraphs are here in the blue circle, and the product subgraphs are here present or presented in the pink circle. We now exclude all subgraphs that are present on both sides of the reactions because these are the structures that have not been changed during the reaction, and we would like to get the information about what changed during the reaction. This leaves us with all subgraphs that are either only present on the reactant side or only present on the product side. And the information which kind of subgraphs are only present on one side of the reaction is encoded in a binary vector, which we can use as a reaction fingerprint vector. And of course, we can also train a transformer network with the reaction smile string as the model input with the aim of generating meaningful reaction representations. Here we are looking at the RxNFP model, which is a transformer network encoder that can process such reaction strings. To use such strings as the input for a transformer network, we have to tokenize it, and this works exactly as we have discussed for small molecule smile strings. In the case of this model, the tokenization was done based on the SMILES specification rules. This RxNFP model was first pre-trained on many different reaction SMILE strings for the mask token prediction task. And as it is typical, this was done by randomly masking 15% of the tokens in the input sequence. Then the model was fine-tuned for the task of predicting reaction classes from the input SMILE strings. This fine-tuning was done on a dataset consisting of 2.6 million reactions and with a total of approximately 1,000 different reaction classes. The model architecture is an encoder-only transformer network, and the model size is surprisingly small with a hidden dimension of d equals 256 and only 12 encoder layers.